it says factor, and then when we look at the exponents with the 3/2, the 1/2, and the -1/2, they aren't nice numbers. So once again, if we factor out the smallest exponent, in this case would be an x to the -1/2, out of everything. And I also notice that in each of those terms, 3, 6, and 45, there's a common factor of 3. So I could factor that out as well. So as far as numbers are left, are you okay that there's going to be a 1 here, a -2 here, and a -15 there? Just going to put those there because that's the easy part, taking the 3 out. When trying to figure out how many x's are left in this first one, should it be x to the 1, x to the 2, x to the 7/3? One of the ways that's really helpful is to think about using your exponent laws and saying, if I multiplied a -1/2 times something here, I need to get 3/2. And when you multiply exponents with the same base, you add the exponents. So what would be here that if I added -1/2, I would get 3/2? Okay? So some of you can see that it's 2 already. I could write, if I wrote it as 4/2, that's the same as 2. Can you really see that when you add those, you get 3/2? So I'll write it like that for now. If you knew it was 2 right away, simplified, perfect. Same thing here. If I go to the next one, I'd say, well, what would have to be here? X to the what to get 1/2? -1/2 plus 2/2 would give me +1/2. And of course, in the last one, you factored that x to the -1/2 out, so it wouldn't be there anymore. Now, I added that as an extra step. Most of you would just go to this right away and write x squared minus 2x minus 15. And now we can factor this using our old methods of factoring. To get an x squared, it's going to have to be x and x. What are the numbers that would work to give us a -15 and still give us a -2 in the end? You see it will be 5 and 3. The 5 will be negative and the 3 would be positive. Again, whenever you factor, one thing you should always do in your head after you factor is multiply it out. Okay? I do it every single time. After I do it, I quickly multiply, right? X times x, x squared, -5x plus 3x, -2x, -5 times +3, -15. Perfect. I know that it works. Okay? But math teachers don't always say what they do in their head. They just say, okay, it's good, let's keep going. You're like, what? How do I? But it is good practice to be checking that as you go. So this is new factoring. Something with a little bit different, with negative exponents and x to the -1/2. The idea that we talked about yesterday, right? Factor out the smallest exponent as a common factor. Then hopefully you can factor normally. It might be that you do that and it still can't factor, but at least it changes it to something that you're more familiar with. Some more review. Do you remember factoring with synthetic division and the factor theorem from grade 12? No. All right, good. Then we get to review it. Have you done that yet in grade 12? No. Well, then you get to learn something new. So the factor theorem, which you're going to learn in a month or two, tells you whether or not something is a factor. And it's based on the following idea. Okay? I don't know what the factors of this are, but let's say this factors nicely to being, okay, I'm going to make up numbers that don't work here. Maybe they work. Maybe they don't. I'm just making up stuff. This isn't the right answer. There's a chance that it's the right answer, in which case I would be very, very lucky. But most likely it's not the right answer. Okay? But what this would say is if you made this equal to 0 and tried to solve for x, 3x plus 2 and x minus 1 and x plus 5, would you agree that minus 5, 1, and negative 2/3 would be the answers? So the factor theorem uses this to work backwards. It says if these were the answers, then if you plug in 1, if I plug in 1 into here, this middle factor will be 0, and anything times 0 would give me an answer of 0. That's why it's an answer. So the factor theorem works backwards. It says if you plug a number into here and it makes it equal to 0, like if I plug 1 into here, I get 3 plus 4, which is 7, minus 9 minus 10, which is negative 12, does not equal 0. So I right away know I actually, in my guessing, this is wrong. I hope you haven't written anything down so far because I'm just making stuff up. Okay, great. I won't make up stuff all semester, but just a little bit here and there. Right? When I plug in 1, if it was truly a factor, it should equal 0. Okay? Now with the factor theorem, it uses something you know with foiling and with multiplying, that whatever numbers are your last numbers here, they have to, in the end, multiply to give you your last number there, minus 10. So I was correct in choosing 2, negative 1, and 5 as a possibility. I just guessed wrong. So when we use the factor theorem, we take that idea and work backwards. Right? I already talked about trying positive 1. And when I plug positive 1 into f of x, I get 3 plus 4 minus 9 is negative 2 minus 10 is negative 12. So that tells me that x minus 1 is not a factor. If I tried negative 1, and this you can write down because this is good, this is back on track. If I try negative 1, I would get 3 times a negative 1, negative 3, plus 4, plus 9, minus 10, and sure enough, it equals 0. And that tells me that x plus 1 is a factor. The numbers that I tried, like you might say, Mr. JR, why did you try 1 and then negative 1? Whatever numbers you try have to be factors of negative 10, the last number. Because if something is a factor, all of those last numbers would get multiplied to equal that negative 10 in the end. So once you find one factor, then if you want to factor it completely, you get to use synthetic division, which is also something you're going to learn in the grade 12 course if you're taking it at the same time. So synthetic division looks like this. You take the coefficients of the term you're dividing by. In this case, we have 3x cubed, 4x squared, negative 9x, and negative 10. You take the fact that you know that x plus 1 is a factor, and you put the 1 with the opposite sign out in front. Bring down the first number. Negative 1 times 3 is negative 3. And add. 4 plus negative 3 is 1. So the step in between is this number multiplies there and goes there. Now we repeat this step over and over and over again. So now I would take the negative 1 and multiply it by the 1 and put negative 1 there. Again, I add negative 9 plus negative 1 is negative 10. I multiply again. If you were right and it was a factor, you should get 0, because that last number represents the remainder. And the numbers that are left represents what you get after dividing. Because synthetic division is dividing, and what we've done is we've figured out that f of x, which was originally the 3x cubed plus 4x squared minus 9x minus 10, we have in fact factored out the x plus 1, which we knew was a factor, and the synthetic division says what's left? 3x squared, 1x minus 10. So the numbers that you get at the bottom of synthetic division is what you would get if you factored that x plus 1 out. And if you multiplied this out and checked it, it would get exactly what we started with. We do synthetic division until we get to something that is squared, because then you can use your old factoring techniques to factor the rest. So to get 3x squared, I know it has to be 3x and x. To get 10, it could be 10 and 1 or 5 and 2. It makes a difference if the 5 and 2 is here and here or here and here. I'm going to put the 5 here and the 2 here. Because then my outside is 6 and my inside is 5 if I was checking it. And if I want a plus 1, I would want plus 6 minus 5. Quick check, does that give me minus 10 at the end? Yes. Does it give me 3x squared? Yes. Does it 6x minus 5x give me plus 1x? Yes. And now we've factored it completely. So the factor theorem in synthetic division, that's a little bit of review from grade 12. Again, what we're doing right now is a big part of limits is being able to factor to simplify things. And so we're just reviewing all of the factoring techniques that we've had so far. Okay, a little joke. What's this? My Halloween costume wish list. They're the scariest costumes I could think of. Vampire, zombie, math teacher. Long division gives me the willies. Now, synthetic division and long division are the same sort of thing, so that's why it's here. All right. Something you did not take in grade 12, well, you kind of did because you could use the same techniques, but it comes up a fair bit in university and calculus, is special factoring of cubes. There's a difference of cubes just like there's a difference of squares. There's also a sum of cubes, and they can always be factored this way. So again, this might be something that you know, to remember it, you might memorize this. As far as figuring it out, for x cubed minus y cubed, to help myself remember it, I remember that one of the factors is x minus y, whereas for x cubed plus y cubed, one of the factors is x plus y. They seem to go together, x minus y with this one, x plus y with that one. When trying to figure out what it goes with, because I don't memorize this, every time I have to do it, I have to think back and figure it out again. So how do I figure it out? Well, I know that I need to get an x cubed. So the only way that's possible is if my first terms are x and x squared. I know that I have to get a y cubed. The only way that's possible is if this negative y hits a positive y squared. That same strategy will help me with this one here and this one here. Now for what goes on in the middle. If you were multiplying this out, okay, if you were using distribution, I mean this x hits the x squared, it would also hit the y squared, it would also, hit the xy, hit the y squared, this y would also hit the x squared, and it would also hit the xy. So if I've already figured out that this has to be y squared, and I think, what's going to happen here when my x hits that y squared? I'm going to get an xy squared. That needs to go away, because what am I left with after I multiply everything out? X cubed minus y cubed. So then I'm thinking with this y here, what would have to go there to get a negative xy squared? Well, if I'm multiplying by y, it would have to be a positive xy. So now I'm going to redo that without the numbers there. So I'm on my test, I see a difference of cubes, and I'm like, oh, how do I factor those? Because this is not on my formula sheet, and I have to remember this. So I say, okay, I remembered that it was x minus y times something. And if I wanted to get an x cubed first, I would need an x squared there. And if I wanted a negative y cubed here, I would need a positive y squared there. Because then my negative y hits. I think about there's something in the middle. If this is all multiplied out, there has to be something in the middle so that they all cancel out in the end. This first arrow gets my x cubed. My last arrow here will get me a positive xy squared. So in order for that to go away, right, I can also make a note that this here gives me a negative x squared y. I need those to go away. So in this arrow in particular, I'm going to get negative y times something, and I need it to cancel out with one of those two. If I make this an xy and I make it a positive xy, then this branch will become negative xy squared. And those two would cancel each other out. I now need to check, does that work? Because I still have one more branch in here. I have, let's go with that color. This branch right here, x times xy becomes x squared y. And I notice that that one and that one will also cancel out. So I've sort of used my logic of how I know things multiply to help me figure out if I haven't memorized it. If that seems too much work, be like, I'm just going to memorize that. That's going to be easier for me to memorize that, then go ahead, right? But if you want to, if you're like, I'm not quite sure and you want to figure it out, you can always figure it out logically through that. Same thing with x cubed plus y cubed. So then we've got these formulas, and now we can get to some questions that involve factoring differences of cubes or sums of cubes. So So you have to be able to recognize that in this case, x cubed minus 8 is the same as x cubed minus 2 cubed. So we go to factor it. It'll be x minus 2. You will get x squared here and 4 there. And then in figuring out what needs to be in the middle, or maybe you just applied the formula. So you memorize the formula. Right? My x is x, so that's easy to apply in the formula. My y in this case is a 2. So here, when I have xy, that'll be x times 2, so I could just write 2x. And here, where I have y squared, it'll just be 2 squared, so I could write 4. The hardest part in factoring a sum or difference of cubes is recognizing that you have that. So in this case, I've got 8 cubed plus 27b to the 6. How could I write this one? Is easy to notice it's a cube. What do I have here? So it could be a sum of cubes. What would go in the brackets? It's got to be a 3, because 3 cubed is 27. And b squared, b squared, b squared, b squared, would give me b to the 6. And now I can go and, right? Move it over so I have enough room. It's plus, so it's going to be a plus 3b squared. I'm going to have a squared here and 9b to the 4 there. My middle one will be minus 3ab squared. Again, if we write out the formula right underneath that, well, x plus y cubed, let's write it out nicer. X plus y cubed is equal to x plus y, x squared minus xy plus y squared. Just plugging things in. This time, what's my x? It's a, so I get a. What's my y? It's 3b squared, so I get plus 3b squared. X squared would be a squared. Y squared would be 3b squared times 3b squared, 9b to the 4. And then here they get multiplied together with a negative sign, and we write negative 3ab squared. Proper notation for writing monomials, alphabetical order. That's why the a came before the b. You won't get deducted marks for that, but you're going to notice that in your textbook follows all the old rules of simplification all the way through. There's about, I don't know, 100 rules for simplifying in math, maybe more. Probably simplify is one of the most complex math words that exists, because there's like, you have to know how to simplify fractions. That one you're like, yeah, I got that, right? There's simplifying radicals. You can't leave something as the square root of 20. You have to write it as 2 root 5. That's simplifying radicals. There's simplifying fractions. You can't have a square root in the denominator. There's a whole bunch of simplification things, which makes it complicated. And the textbook in the answer key always has, quote unquote, the simplest form of every type of algebra you could imagine. So it's going to be really good practice for us algebraically as we go through. Okay. We've got a couple of more things that are going to be sort of background setup things for limits. back in grade 11 with radicals, you learned that to simplify, you had to rationalize the denominator. And one of the things for rationalizing the denominator was something called multiplying by the conjugate. Now, the word conjugate is complicated in math because you hardly ever use it, so you forget what it means. And when you forget what it means, it also makes multiplying and simplifying harder because you forget a word. So one of the things that we try to do in mathematics is when we come across a new definition, like the word conjugate, we spend a lot of time trying to grasp that concept, because if you know the word, your chances of being able to do the math increase greatly. If you're like, oh, we have to do that thing, then your chances of remembering what to do decrease. So a conjugate for math, when you have a binomial, is the same numbers, just the sign changes in the middle. That's what the conjugate does. And the reason it's there for getting rid of square roots is because if you multiply two conjugates together, x minus y and x plus y, you have a difference of squares. And when you multiply that all out, you always have the middle things cancel out, and you just get something squared minus something squared. If one of your things was a square root, and you square it, it goes away. And so that's the beauty of multiplying by the conjugate, because you can get rid of square roots. And we're going to find in limits that one of the things we often have to try to get rid of are square roots. And we don't only do that by rationalizing the denominator. Grade 11, you rationalize denominators. In grade 12, in this calculus class, sometimes you're going to rationalize a numerator and move the complicated stuff into the denominator. And you're going to see where this comes up and why it's helpful. But for now, we're just going to look at what that looks like. So in this first example, I have in my denominator a binomial with a square root. If I want to get rid of that square root in my denominator, I could multiply by the conjugate. What does that look like? Well, the conjugate would be same first term, same last term, with a different sign in the middle. And if I multiply the bottom by that, I have to multiply the top by that. Because what is the value of what I've written in green? Just the green part, what's it equal to? It's equal to 1. How good are you guys at your 1 times table? Have you been practicing? How high do you have it? 15? No, higher? Good. 17 times 1? It's good. Okay, multiplying by 1 doesn't change anything, right? If you only had to do your 1 times table all through school, it'd be like, oh, can't wait for this exam. This is going to be awesome. Oh, they thought this was a tricky one. 82.3 times 1. Got it. 82.3. And you'd be like, I'm so good at math. All I need is my 1 times table, and I'm set. But in math, multiplying by 1 is powerful because it doesn't change what it's equal to. It just changes what it looks like, right? If I have 3/5 and I multiply by 2 over 2, I get 6/10. 6/10 is still equal to 3/5, but it looks different. Same thing here. When I multiply by this, it's still equal, but it's going to look different. In my numerator, if I distribute, I'm going to get 2 square root of x plus 3 plus 4. But in my denominator, if you look at these, it makes a difference of squares. And so I will get the first ones squared, which will just become x plus 3. And I will get the last ones multiplied together, which will be minus 4. And so this simplifies to 2 root x plus 3 plus 4 divided by x minus 1. And now we no longer have a square root in the bottom of our fraction. I would like you to try this one. I'll put the answer up so you can check how you did. How did it go? All right. And so the last two examples that we have are the same thing, but with rationalize in the numerator. And the first one is interesting. So I'll do it quickly with you. It's the same idea, but now they say, can you rationalize the denominator? So I'm going to have square root of x minus 4 over x minus 16. And my question is for you, what happens when you plug in 16? It's equal to 0? Are you allowed to divide by 0? Got a little bit of a problem there, don't we? If I plug in 16, I'm going to divide by 0. And dividing by 0 is bad. This is what happens to your house. You can come look at it later if you divide by 0. Okay? Don't do it at home. It's dangerous. Okay? So you can't divide by 0. But I could put in 15.9. What would it equal to if I put in 15.9? What if I put in 15.99? What do we get close to? We're going to find out. So first of all, I'm going to rationalize the denominator here. Okay? So I'm going to multiply by square root of x plus 4 over square root of x plus 4. I'm going to multiply this out on the top. This simplifies nicely to x minus 16. On the bottom, I'm going to have this times this, but I'm not going to multiply it out. And the reason I'm not going to multiply it out, hold on a second, this is going to get exciting, is because then I'd have an x minus 16 times a square root of x plus 4. And what happens to those x minus 16s? They simplify, and we're left with 1 over the square root of x plus 4. Now, are you allowed to plug in 16? Yes. If you plug in 16 now, you get 1/8. In fact, if you plug in 15.99 into that question, you get really close to 1/8. And that's the thing that we're going to do with limits. 16's not allowed, but we're going to ask, what happens if you plugged in something really close to 16? 15.99999999999999999999999999999999999. You would get really, really close to 1/8. And that's going to be our idea of a limit. Okay, so at the end of this section, there are some questions out of your textbook to practice. Some factoring in there, and again, make sure you check your answers in the back. Have those done for tomorrow.